Greetings wherever you are, and you're welcome. Today, we want to look at how to visualize trees, different kinds of trees, and then what is it in R programming. But just to give you a background as to what trees is all about, if you want to learn, if you want to do machine learning in R, we have something called supervised learning and unsupervised learning. Okay. Under the supervised learning, there are several algorithms in which we use to be able to, do our machine learning or build our model. One of them is random forest, another one is decision tree and whatsoever. But should I surprise you? This decision tree thing, it came long ago, very, very, very long time ago. It's not now. So let me pull up this. Now, can you see this? When we were in primary school, these were the things that we learned. So here we have 100. So 2 multiplied by something should give you 100, and that will be like 50, right? And then we have 25 here. So what do we put here? Then we are going to put something like 2. Multiply 2 by 25, that will give you 50. And then we have 5 here. And what are we going to put here? We're likely to put 5. So 5 times 5 will give us, let's say, 5. Then in that order, this is what we call decision tree. Maybe I could pick up another one and then you look at it. But in primary school, we call this factor, or what is it, or factor tree or something like that, if I can remember. But it's very, very important, and it is used in building a lot of models. This basic thing that you are looking at is used in building so many models. And then what it does is that, now let me pick this one. So let's say I am looking for, I am building a model, and that model is supposed to predict something. And so this is my root. This is why I am, I am starting. And I'm saying that if the number is 2, ignore it and move to, 32. And so at 32, if the number is 16, or if the number is 2, ignore 2 and then move to 16. At 16, if the number is, if you check 8 and then 2, then that will give you 16. So ignore 2 and then go to 8. In that, up to the last number that you are looking at. So it's like you have several categories of things, and then you are looking at you are looking at some comparison. You are saying that, okay, you have so many people that you want to classify, or you want to categorize or group. We are saying that if the person is tall, then pick the person. So it means we have exempted all the short people. Then we move again and we say that if the person is dark, choose the person. So even though the person is tall, but if the person is dark, you choose. So we have ignored all the fair people. Then we move a little bit and we say that if the person can speak more than 5 languages, pick the person. So all those who cannot speak, we ignore them. That is what we call a decision tree. It allows you to be able to follow in, or to be able to exempt all those that will not fall in that category. This is very important in machine learning. So today I want to try my best and see how we'll be able to see this in real life situation. I will try my possible best and see how we can build it. So here, I'm just simulating the data. For the sake of time, as you can see, I've already built some of the trees. I just want you to have a feel of it. I'm very poor at colors, so please pardon me when you see my colors are not bright. I don't really know how to choose colors, and so these are some of the trees that you can see. So I have another one that's here. I'll show you how to be able to do all this. It's not really rocket science. It's very simple, and then this is something that you have. So now let's begin from somewhere. So first of all, if you are building a tree, the most important thing is you have to first of all have your data. And like I've said, apart from the decisions that you are taking using a tree, it is also used for evolutionary studies. So it allows you to be able to track where you have inherited a gene or you have inherited a particular characteristics. So let's assume that you are in a company. In your company, you are about 30 people, right? And then all the 30 people, you have decided to pick all their traits, the way they talk, the way their eye color, their weight and their size. you can use a decision tree to put all that together to see how each of them, I mean, how many of them are closer and much more closer in terms of their physical characteristics as compared to the others. So now, first of all, what do? You have to pick those data points into a data frame. So here, I am creating a data frame. I'm just going to run that. So I am creating a data frame of 60 variables from 1 to 10. For now, it will make sense. If I print the data frame, you won't see any sense in it. So this is what the data frame will look like. Let me roll this up. So I just pick the, what is it, and then it won't have any sense. It doesn't even have headers. As we go, you are going to see how it works. So the next thing is I decided to round it up. I just decided to run line 7 to round it up so that we can have some integers. So this time around, when I build it, we can see that all the data frame they are now integers. To 1 decimal places. They are just numerals. And so what do we do? The next thing is I want to give them some names. I want to give the columns. You see that the columns we don't have column names. These are the column, and then there are no names. It's just the functions that I have used in creating those columns. So I've decided to give each column using this function called pastes. So what I'm done here is that I'm going to say, how many columns do I have? 1, 2, 3, 4. So I'm just saying that column 1 should be Gene1, column 2 should be, and so that's why I'm using the function pastes, and then this, and then it will be separated by underscore, and that is it. So if I run that, so I'm using the function column name to name all the columns inside this particular data frame, and then that is it. So if I do that, I run it, this time around when I print, you'll see that it will now have column names, as you can see. So the column 1 is your Gene1, Gene2, Gene3, Gene4. Right. So the next thing is I need to give it, I need to also have some row names. How many rows are there? I think about 60, right? So what I'm going to do is I'll say row names of this particular data frame here. And then I am going there to say, okay, use the paste function. And I'm saying that I have bacteria. And so that will be 1:20. And then I have the second one that is also bacteria. But the first bacteria is just only bacteria. The second one is bacteria star. And then the third one is bacteria underscore. If you put that together, that's how we are going to name all of them. So we use the paste function. So it will be bacteria 1 all the way up to 20. So we're going to have bacteria 5 up to 25, 24. And then we have bacteria 12 to 31 in that order, just to make sure that they are all at random. But bacteria 12 to 31 are all having underscore. So when I do that, if I run that, it means the data will now have column names, and then it will also have row names. So now if I print it, that's going to look beautiful, right? This is quite simple. So now I have my bacteria here. I have their genes here, Gene1, Gene2, Gene3, and then Gene4. That is just very simple. Now, the next thing in building a tree, phylogenetic tree, is you must make sure that you create what we call distribution. And so this is a data frame. So once it is a data frame, now let me come down this way and just demonstrate this. So I have my data like this, which is standing here. So if I should bring something like this, I have separated the rows and the columns. Rows to this side, and then columns on the right-hand side. So what I'm simply saying is that I'm going to that particular data set, and then I want to pick either all the rows, and then go and pick a certain number of columns, and then I will simply just assign something called diagonal using the function distribution. That's all. The distribution means that is how I want the data to be distributed in a diagonal form. So it will slide each of them in a diagonal form. And so that's all that I have done here in this particular one. So I'm going to create a variable called distribution and use the function distribution and say, go into the data frame, pick all the rows. That's why the rows here is empty. And then go to the columns and then pick all the columns, 1 to 4. Maybe that is because they are all 4 columns, but in some cases, I just want to select, I'm not interested in all the columns. I'm just going to pick this, and I'll go there and say, all right, diagonal is equal to true. Diagonal is also a function that's equal to true. Sorry, it's an argument come under this function called distribution. So when I do all that, I pack the data into this variable called distribution, which is okay. Now, the next thing to do is to build All right, so what is it? I had a power trip, and that's why it went off. Sorry about that. Great. So this is where we were. So I was saying, so I've packed all that we have here. I have created the distribution. By way of those who don't know, we created a data frame, and then we went ahead to create the next thing is distribution. And the distribution simply means that that's how we want to slide it. So we just say diagonal is equal to true, and then we pack it into a new variable called this. So we are building a tree. And so when we have done that, our distribution is ready. So maybe I should just print it and let's look at, you see how the distribution is going to look like. If I fold it up, you see how. So it's going to be, it's a whole lot that you see the way it has slided because I said diagonal. So it will slide it according to those that are a little bit closer. All right. So that's what happens. So the next thing is to make sure that we build something we call clustering. Clustering here means that we're going to allow those that are having similar values to be able to cluster together. And those that are having practically the same values will be much more of like the closest siblings as compared to the others. So we use a function called hclust to be able to do that. So an hclust works with after the data has been distributed. So we use the distribution variable and put it there, and then we run that particular line, which is line 24, and then we have finished that. So when we are done, we can as well maybe change the hclust into something we call as dendrogram. But and then so I am building my dendrogram as so basically we are changing all what that was here into a dendrogram, and then we can have our dendrogram. And then now we can now visualize to see how our data is going to look like. And so I can simply plot the dendrogram and then look at how it looks like. So our tree it has been built. And then that is it. So it's very simple to be able to, so we can now see which of the bacteria are closer and look at, if we're building a phylogenetic tree, you can look at how it looks like. So this is our bacteria 6, bacteria 15 star, and then we have bacteria 17 bacteria. So bacteria 6 and bacteria 15 star are much more closer. They are closer siblings as compared to the others. So in terms of the genes that we have, the gene values or the allele values in the genes that we have created. And that is basically how we are able to build a tree. Is so at a point you need to pause the video and see whether you'll be able to understand it. And that's what we are saying. So if I had come here, now let me run this again and then check something here. So we are looking at, look at bacteria 16. So now let me pull this up a little bit. Bacteria 6 and bacteria 15 star. So I'm going to minimize this. And so I'm going to look for bacteria 6, which is here. Bacteria 6 is here. It has the gene 1 is 1.1, gene 2 is 9.0, gene 3 is 8.2, and then gene 4 is 1.5. I'm going to look for bacteria 15 star. Bacteria 15 star is also here. So you notice that they are a little bit closer because of the kind of distribution that we have given. And that is what is making them quite closer. So look at their genes and then their allele values, and then that is what has made them to cluster or to have come from the same place or to be coming from the same place. Remember, this is a simulated data. And then, so this is how we create it. So we, first of all, have to have our data frame of all the variables we want to create. The second thing is that we have to create a distribution, and then you know what the distribution is. It takes, you just select your rows and your columns that you want it to be part of the distribution. Then you will go ahead and then create and then use this argument called diagonal, and then you are good to go. And then when you have done that, you use your H-cluster to be able to cluster it based on the distribution that you have done. And then you can convert the H-class or whatever variable into a dendrogram. And then you can plot the dendrogram, and then you are good to go. And even you can also plot the H-class. For instance, here, I could have just gone ahead to, let's say, plot the HC underscore T, which is there. And then that one too would have also given you, yeah. So this would have given us what is the cluster dendrogram. And it looks like this is much more clearer than the first one. There's a difference between dendrogram and then a phylogenetic tree. What we have done here is a phylogenetic tree. The dendrogram, even though they are the same, they would have given us the same thing. It's the same bacteria 6 and bacteria star 6 here, which we can see. But you realize that in this one, what is much more distinct. So as we can see, we have a whole cluster here, another one there, another one here, and another one here. And that is it. So this is a beautiful phylogenetic tree. Now let's check. What is it? Let's see whether if we can build another one. And so here, I am saying that, like those of us who are in microbiome studies, so we have just created, let's say, like a microbe. We're using this function. What is it? A microbe. And so all I am saying is I'm just going to explain only this, and then. So we are creating a sample, and we are calling it microbe. And we are saying repeat microbe. How many times? 24 times. And then we are going to also say that we are repeating microbe 24 times, but we want to give each microbe as microbe 1 all the way to microbe 24, separated by nothing. And that's all that we have done there. So when we do that, so we're going to have, if I come to print out this, you're going to see that we're going to have microbe 1 up to microbe 24, separated by underscore. And then that is it, because I had already indicated that microbe underscore here. That is why you are seeing the underscore there. So now we have that. So I'm just going to run all the way up to this place. And so when I do that, it runs properly. And what I've done here, I've created these 3 vectors. I decided to create a data frame out of it, and I'll call it microbiome. So I decided to use a function, a for loop, and I say that for I in sequence 1:5, then don't mind me for that portion. So we're creating a gene, and then and we are sampling just 1 to 40, 24 of them, and then we put it here. So we want the gene to have different numbers. So it can, what is it? So we're going to have a gene. So if I run that, I'm going to run the whole for loop, but I can just print only the gene, and then you see what is going to happen there. So you can see that it has selected some numbers at random. So what we have simply done there is that we have given some random number 24. So the gene will have, like a gene can be 39, maybe that's the allele number in that order. So we also decided the microbiome here, we bind it with the gene. So we've added this gene as to the column, to the data frame called microbiome using cbind function. And that's what we have done here. It's the same thing. And then we column names it. So we just create a column names here because we are using a function. We use this and we are pasting gene and we are saying that I is to, and so that's going to be our column. So the columns is going to be column. This is just the same thing as what I've done first, but I decided to incorporate functions there for us to see how it works. It's the same thing. And so now I come here, I decided to, now give some kind of treatment in terms of colors and whatsoever. And so I can't just pause the video if you're not getting it. And then I don't want the video to be extremely too long. And so now I'm finished with the data part. So now if I pull up the data frame, you can look at how it looks like. So I have sample, I have species. So I decided these are my row names like I did the first time. Then I have my column names. I have added some few columns to it. So I was already having sample species treatment. Then I added gene 1, 2, 3, 4, 5, and then in that order. And then my data frame is ready. The next thing is to simply create a distribution, just like I said first. And so here we are creating a distribution, but we're using all the rows, and we are selecting only from the fourth column to the eighth column, and we are using diagonal argument. And so when we do that, it is created. Then we use our H class to be able to make sure that we have our clustering. And then we convert it to dendrogram, and then we plot it. And then you can see that our tree is also here, which is very, very simple. Like I keep saying, if you plot as a dendrogram, you may not see the clustering properly. But if I come here and then I decide to plot only the HC like this, that is always a little bit better here, like this. So you can see how the clustering is done. So the microbe is here, then in that order. So maybe I may want to add colors to them. So I use this particular function called HDC, and then it's able to select. And then I can go ahead and then use a function because I am going to select each of them and then give it an attribute. So I'm giving a function called n, a function with an argument m. And I'm saying that if it is a leaf, of this particular argument called n, then we're going to assign attribute of n to a, and then we come and use this function, match the attribute m, and then label it a microbiome in the first column. That's what we have done here. If you're not getting this part, you need to go and watch my video on functions. And then when we finish, we'll return m, which is our argument. So now when we finished, we simply apply this function we call dendo apply. And so we select what we already have here, and then we use the color. All these, I have created them inside here. And then when we run that, we are good to go. And then we can now plot our dendrogram, give it a title, and then with all these colors which are there, we are good to go. And so now when we pull this up, you can see that our colors are now quite beautiful. We can see that we have decided to give the microbes different colors based on their clustering and whatsoever. Now, we can add a legend to it so that the colors will make sense. So we added a legend, and then if I come here, you can now see I have antibiotics, non-antibiotics, fungi, bacteria, then in that order. And you can see how it all works out here. So now if I see a microbe, I can know whether it is resistant to antibiotic or not, and then in that order. And so we've clustered them accordingly. So that's also, now let's quickly do something here. I've already, I'm into, these are just data that I simulated. I tried to let you look at it. But in real life situation, we would have a data that maybe you work somewhere, then you have picked up your data. I have this data set. If I go to my desktop, I'm going to my Excel. I can go to the multi-local sequence typing data. So I'm going to open that for you to see. So these are strains. what is bacterial strains that I have, I have worked on, and different from Sudan, Nigeria, and whatsoever. I picked up their housekeeping genes, right? There's the 7 housekeeping genes which are here. The housekeeping genes are here, and these are their allele numbers. All these housekeeping genes these are the allele numbers at all the locus positions. So I wanted to see which of them may cluster together, which of them might be having the same ancestry or evolution. So I needed to generate a phylogenetic tree or to just generate a tree from this. So I have to take this to R and see how I can visualize it. And so let's go to RStudio. So I simply say, because it's a CSV file, I save it as a CSV file. I'm going to read it. I think I've already read it. I don't know if so. If you run this line, it's going to take you to your. If you follow my tutorial, you should know this. To take you to my local computer, then I can choose the file. Because it's a CSV file, I'll choose that particular file. Then I packed it to this. So here, if I do that, you can see I pull this up. You can see all of them are here. So you notice everything is here. So everything is here. And that is it. So the next thing is to make sure that I have the row names, which I have already done. Then, so if I run here, what I'm simply saying that the row name should be the column 1. The column 1 should take the row should become row names, and then in that order. So now if I run that, you can see that column 1, you can see I now have this as a repetition. This is the strain, but the same strain is now the row names. And then I already have column names, so I don't need to do anything about it. So I'm just going to go ahead and then create my distribution. Here, I am not interested in all of them because there are too many. There are too many, but so I'm just picking from row 1 to 40, and then I'm going to run that. Then I do my age class. Object D, not okay. I mistakenly highlighted the D. And so the age class is there. I can convert to dendrogram. Then I plot the dendrogram and give it the color green, which is not affected. And so look at how it looks like. So that's how it is. But this is not too clear. When you plot the HC direct, then that is always quite clearer. And then here we can see how the data, what has been clustered. Maybe I should change this place from 1 to 100. 100, maybe the distribution, and then what I check this a little bit so that maybe I will involve all the strings. At this point, they are not too visible. Let me plot the H class itself, and then we are good to go. And then this one is a little bit clearer. So you can see those that are clustering together and those that are not. All I need to do is to reduce the font size of all the the strains and their names which are here. But you can see all the strains that are coming from Cameroon clustered together. But even at that, we have those that are much more closer. And then we also see South African strains clustering together as compared to the North Africans and then whatsoever. But we can see their genetic distances and everything is being measured. I could add bootstrapping, be able to get this done. Now, another one that I would like to do, and that will be I think that will be the last one for today, is just here I use a CSV file and I converted it. In this case, there are also instances that you would have built your tree already. You would have built the tree already, but you want to now use R to be able to make sense from it. Okay. So for instance, I have, if I go to my downloads, I can go to Mycobacterium, the new one. So I've already run this data and I have my Rory resource. And then I have this called Newick tree. This is a Newick tree. Okay. This Newick tree, I can import it to R, and then I'll be able to use that to visualize or to generate the phylogenetic tree. For instance, this has been built already. I use a different package to be able to do that. So now how do I get this into my R? and then I'm able to work with it. So how do I do that? I use this function called read.tree, and then to go and choose it, to go and choose that particular file over there. Now, what is going to happen is here, to be able to do this, you need a package called apes. Ape, or you can use ggtree. You can also use ape. If you don't have it, you need to install ape. Then you library ape. That will allow you to be able to use read.tree. I've already read the tree into this. And so you can see, let me fold this up. So this is how the tree looks like. Remember, it's a tree. You're not going to see it like the way the data frame looks like. And so I'm just, let me pull this up, pull this down a bit. And then, so I've read the tree there. The next thing is to root the tree. So I've read the tree into this variable called my tree. So I am saying that reroute the tree, and I'm saying root that variable my tree, and you still pick that my variable my tree, and then you select the tip dot label, and then what is it? You give it this particular whatever value of an index 9, and then that is it. And so when you do that, we have rerouted the tree. Then we'll go ahead and then plot the rerouted tree, and then we give it this particular note. And then when I do that, now come and have a look. This is how it's going to look like. So if you have your weak tree already seated, you can import it into R using ape, the ape package. Install the ape package, load it into your R library, and use read.tree function to be able to import it. And then into bracket file.choose, so that you can go to your local computer and choose it, the file. Then when it comes there, you just simply reroute it, and you are good to go. You plot it this way, and so you have your tree, which is ready. You could have converted it into, and then perhaps I give it a node which equals to 2. I could have added some labels to it, but if I add this label, it looks so bad. I don't really like what to add it. So here, what am I doing here? I'm trying to create different colors, you know. And so what I do is I create a variable called age color, and then I just create an empty vector and assign it to it. An empty vector. This is how we create an empty vector assigned to it. And so now with this particular empty vector, then I go into that particular age color, and I say 1:20. Then I mark everything to this color called gray. So now I also created some random colors which are here. Then I marked it and I gave it a variable. And then I say the tip of the phylogenetic tree, I'm assigning the color here. I think this is repetition. I could have just done this. And then that is all. So I'm assigning this particular variable here to this what called tip call. And then that is it. I think it's repetition. And so here I am ready. I can now plot my rerouted tree, which is here. Then I use, these are functions. Immediately you use a plot, and then you are using a tree function. So there's this argument called use.edge.length. Then you say true. And then the tip.color, then we give it the tip color. So the tips are going to have color. The edge.color, we can also give it the edge color. And that was the color that we had given here, which was gray. And then we're saying that the sizes should be 0.9. And that's all that we have done here. And then when we plot it this time around, you will see that it's going to be of different colors. I've already told you that I'm very bad at colors, and that is why my my color combination is the way you are looking at. Maybe if we change the gray color, maybe I should have changed the gray color to, I don't know which color I should choose now, because it's like I've chosen almost all the colors. What are the purple, this, what? I don't really know colors like that. It's like there's a color called move. Or, I don't know, purple. And so if I've done this all over again, so I'm going to create this again, run this, run that, and then run this again. So that to take out the gray color and replace it. So here you can look at how the tree looks like. So now we have colors, and we also have the edges. The edges also have their own colors, which is quite, all the edge colors are what? Purple. The first one was what was gray. Now, you could have edge colors, you could have the leaf, the tip colors, you could have the node colors, and then all of them. You just have to create your own colors and then add it. Now, that is, we just plotted the tree. We can plot the tree in a circular manner. So if you want to plot the tree in a circular manner, you specify fan. You specify fan. So maintain all the functions that we have on top here, line 136. But in this case, when you plot, if you say plot circular, so you use plot.phyllo. It's a function, plot.phyllo. It will allow you to be able to, you are plotting a phylogenetic tree. And then you say reroute. That's where we have rerouted that. Remember, we created that variable on top there, followed by fan. Immediately you put fan here, it means you are going to create a circular, phylogenetic tree. And so look at how it looks like. You're going to have your circular, and then with the colors of whatsoever. So it's going to be circular like this. If I widen it up, pardon me, with my 4-color combination. What about radial? If we want to plot it as a radial, then you simply select radial, and then that's, you are good to go. And so let's look at the difference between the radial. So look at how the radial looks like. That's the radial of phylogenetic tree and how it looks like. It's a little bit clumsy if you're not too comfortable, but I can see how the strains are being clustered. And so, ladies and gentlemen, this is how we are able to visualize a phylogenetic tree, or you can visualize all sorts of trees. Now, there are different ways you may want to visualize the tree. It can be fan, it can be radial, it can be whichever shape at all that you want. Once you are using plot.phyllo, I give you all sorts of arguments. You see that if I bring my cursor here, so you can check on this yellow pop-up menu, and you can see all the argument that you can put inside, and then you are good to go. The most important thing is, if the file, the Newick file is already built and it's seated somewhere on your computer, import it into R, reroute it, and then when you have finished rerouting, that's all. If it is also a data frame, you have to make sure that, first of all, create your distribution, create your H class, then you can convert it into a dendrogram, and then you go ahead and then plot it. And then, so watch the video, pause at a point, check all the codes, and then what is it? You are good to go. And that's how it works. Just what the rest of the information here, I think I will be doing that one later. And so that's your video of today. Thank you. My name is Bigba Bright, and it's always a pleasure trying to do this with you. Okay, so somebody was also watching with me. You, Sax, nice. Thank you for watching, and please help me to reach out to more people who are interested in data science and whatsoever. I'll be uploading another video on PC principal component analysis and then binning, because I'm moving towards machine learning. So let's look at how to be able to build all the graphs in machine learning before we can begin to look at it. We'll also look at, I've already mentioned it, binning, and how to visualize a binning data. Sometimes the data is just too huge that it's important for you to bin them, and then you look at how each bin is behaving. Right, thank you. My name is Bigba Bright. This is my contact. I'm from Ghana, specifically in KNUST, and then if you want, let's get in touch. This is